Anna, sorry about that. I had to restart Zoom because I couldn't share my screen. How are you today?
I'm good, thank you.
Good.
How are you?
I'm all right, thank you. Yeah, I found it really hard getting up today.
I know, same.
Haven't had my coffee yet, so hopefully it will be delivered soon.
Oh, I thought you meant like proper delivery.
No, not like Starbucks, no. No, unfortunately. Cool. All right, can you see the warm-up question in front of you?
Yeah.
Cool. I don't think you did FSMQ last year, did you? I can't remember.
No.
Okay.
No.
Do you remember me talking about logs in some lessons though?
Yeah.
And how did the logs go yesterday? How did you feel about it?
Oh, yesterday was fine.
Okay.
But I feel like it's going to get quite a lot harder.
It's actually quite fun. It's actually quite fun.
Oh, fab.
Anyway, people are starting to join, so have a go at the question while you're waiting, Emma. All right, thank
Okay.
you. Morning, Nye. Hope you're well this morning. Little question for you to get going on. Morning, Madeline. Hope you're well this morning. Morning, Matthew. Have a go at the question on the screen for me, please. Morning, Hannah. There's an exam question for you to have a go at while you get warmed up. Morning, Nathan. Morning, Emily. You should see an exam question on the screen. Please put a tick when you've done. Morning, Kate. Morning, Theo. Hopefully you can see my warm-up question. Have a go, put a tick when you've done. Shouldn't take you too long. Morning, Matthew. Hope you can see the warm-up question. Let me know if you can't. Morning, Ben. I hope you're well this morning. Just a warm-up question to have a go at while you're waiting, or while I'm waiting for anyone else to join. Just a couple more minutes, and then I'll put the answer up. Just waiting to see some ticks now from anyone that's done the question. If you want to pop your values of A and B to me in the chat box, you certainly can, if you want them checked. Just 1 minute. Kind of expecting to see some ticks by now. Sorry, oops. Right, okay, I'm going to stop you there, and I'm wondering how many of you are trying to divide your polynomial, or whether you've remembered the factor theorem. So if fx is divided by x minus 2, of course, you can just pop the 2 into your function. And if the remainder is 36, that will be equal to 36. If 2 was a factor, of course, f of 2 would be equal to 0. Likewise, a second statement, if you pop negative 2 into your function as x, you get a remainder of 40. So I did that, and I ended up with 2 different statements. So from the first one, I ended up with 8a add b is 50. And from the second statement, I ended up with negative 8a add b is equal to 34. I solved those simultaneously, and I got there quite quickly. A was 1 and B was 42. So I didn't get any answers from anyone. I didn't get any questions from anyone. I didn't get any ticks from anyone. So are you guys alive and well over there?
Yeah, I was just trying to divide it for ages, and when I realised you had to do that, I just didn't have enough time.
Yeah, I was dividing.
I wondered. So when I chose this question, I thought to myself, oh, I know this is a nice easy question right at the beginning of the exam. It was about question 2 or something. And I reckon as soon as you see that word divided, you're really tempted to do your long polynomial division, or of course your little grid method for division. So that's why I chucked that in. All right. Okay, guys. All right, we're going to do some warm up with logs now. So we're going to move on. So beware of those questions there. Polynomial division is not always needed because you've got the factor theorem to help you and the remainder theorem. Okay, right. So what I would like you guys to do, these are quick multiple choice questions. There's about 6 of them, I think. No, there's 5 of them. In the chat box, privately, please, I'd like you to pop A, B, C, or D for me. Morning, Jim. Right, so grab that chat box, please. To me privately, I'd like all your answers, A, B, C, or D for question 1, please. I've got 3 answers in so far. Any more, please? Okay, right, so I'm really liking some answers of C because of course I've got the power, which I've got the base of my log we were doing yesterday is going to be the base, and then the answer, y is the power, is the value there. All right, so that's what's rearranging logs. Okay, writing as an index statement, I should say, or a power statement. Number 2, I'd like to see your answer for number 2, please. Log to the base e of x is often written as what? I've got some answers coming through now. Lovely, and a lot of you remembered C was the answer because we were doing ln x is also log to the base e. Thank you. Okay, not quite sure what you've written there, Theo. Okay, and the next one, number 3, express y equals ln x in index form, please. Oh, I see. Thanks, Ben. Not quite, Theo. Thanks, Matthew Capstick. Matthew W, not quite sure you're right there. Ah, this is throwing up some interesting answers here. Okay, well done, Emily. All right, so what I need to remember is ln x means log to the base e of x, and that was equal to y. I'm used to seeing it in that form there. So now we've got the base of e, so the power of y gives us x. So your answer should be B. So well done to those people that answered B. Not everyone did, so thank you very much for doing that. All right, number 4. Right, getting some answers coming through now. Be really careful with this now. Okay, so I've got quite a lot of answers of A coming through as 0. That's right, because of course A to the power of 0 is equal to 1. So don't forget that base is the base number on the ground there, and the 0 is that power. Okay, number 5 coming up. This is the last one of these. Good, got some answers coming through already. Okay, not everyone's got the same answer. Okay, 3 different answers I've got so far, but the most common answer that I've got was right, was B, A to the power of 1 is equal to A. All right, so that was B. Okay, thanks very much for doing that for me. Right, okay then, so I'm going to use the chat box quite a lot today because I've got quite a lot of quick fire questions, because when I came off the lesson yesterday I was saying, oh gosh, you know, my lessons are so boring, I'm so sorry, so how can I make it a bit more interesting? All right, okay then, so yesterday we were looking at rewriting log statements as index statements and vice versa, and we were also finding the value of log expressions. Now, these questions that I've got in front of you, you should all be able to do from what we did yesterday. So I'm just going to give you a couple of minutes to see if you can answer these questions yourselves. I would love some answers to question 2 in the chat box as soon as you've got any answers. It'd be really good for me to assess if you can do them. So I'm going to give you 2 minutes to have a go at as many of these questions as you can, please. If you type it in the chat box, I'll give you instant feedback. That's right, Ben, good. Yep, That's right, Ben. Good. That's right, Madeleine. Well done, Ben. Matthew Capstick. Ah, you've just written the question down there. Yes, Emma, it is. Matthew Capstick for 2A, not quite. Yes, it is. Yes, it is. Sorry, I was looking at my wrong answer. Yes, absolutely. Ben, I think you need to check your answer to D. Okay, one person. Flynn is joining us. Hi, Flynn. Good morning. Right, okay, I'm going to start going through these questions now. So question one probably definitely the easiest. You've got log to the base 10 of 10,000 is 4, and you should have on the second one log to the base 8 of 2 is a third. Now, yesterday we were looking at how to find the value of a log expression. Whoops, just going to admit Dan. Good morning, Dan. I don't know if you can hear me yet. Hello, Dan. Right, so yesterday we were looking at, we can find the value of log expressions using our calculator. So if we change the first index expression into a log expression, I can write it as log to the base 2.4 of 76 is going to equal x. So if I can change the way it's written, remember the log is the inverse function of the exponential function, I should be able to get 4.95 for that first answer there. So really I'm solving an equation with logs. The second one is just the same. This time I might have to do something with my answer. I've got log to the base 2 of 6 is going to give me 5x. So of course, when I get my answer, I can just divide it by 5. Therefore, what I can say is that x is going to be whatever log to the base 2 of 6 is divided by 5. So if I have a go at that, and if I type that into my calculator, which I did earlier, to 3 sig figs, I should get 0.517 there. If I go to the next one, again, I can rewrite it as log to the base 3 of 1,000, and my answer is going to give me whatever x is plus 1. So, of course, what I could do is I could find x by doing log to the base 3 of 1,000 and subtracting 1 from my answer, which should give me 5.29. So I've got some answers that have come through in the chat box. I can see not quite for some of them. Just got to admit Josh Woodward is joining us. Good morning, Josh. And the last one, I'm informally solving exponential equations here. So I've got log to the base 3 of 20 is going to give me 2x plus 1. So if I get log to the base 3 of 20, and if I subtract 1, and then of course if I divide my answer by 2, I can get my value of x. And if I do that, I should get 0.863. That's right, Matthew. Thanks for sending me that answer there. All right, so that's very, very informal, solving equations that are exponential equations using logs. And we're going to go on to do a lot more of those solving equations tomorrow, where actually we're going to use some laws of logs, which we're going to be doing today. Okay, so I'm going to move on my screen. Unless anybody would like to ask any questions at this point, please unmute yourself and ask anything if you need to, or put a tick if you're happy to move on. Lots of ticks. Thanks, guys. All right, let's move on. Okay, now, I don't mind if you want to grab a calculator. I don't mind if you just want to have a look at these expressions. And we're going to start adding logs together today. And there is a property that you're going to have to learn. Some of you may remember it from last year, FSMQ. So all I want you to do is very quickly, from 1 to 6, yes or a no for each one. You can explore them however you like, with a calculator or not. And I'm going to give you 2 minutes to come up with your answers, yes or no, please. If you want to type them in the chat box, that'll be awesome as well. I don't expect you to know. Yes, Ben, so far. Good. Yep. That's right, Madeline, well done. For those people that are numbering their answers, very useful. Okay, thank you. That was a couple of minutes. All right then. So I'm just going to have a look at the first one, and all I'm going to tell you is that the answer is yes. The second one, I'm going to tell you the answer is no. Let me just have a look at the next one. Definitely a yes. Let's just have a look at the, oh, definitely a no there. Let me just have a look at the next one. Oh, definitely a yes. And the last one, oh, it looks like, oh no, definitely a no. Okay, right then. So what I would like you guys to do now is having a look at the answers that I have given you, which I do believe is right, unless I've made a mistake. I don't think I've made a mistake. But I'd like you to unmute yourselves, please, and I'd like you to tell me any patterns that you notice in these statements.
When the bases are the same, do you just multiply like the big numbers? I don't know what they're called.
Right, okay, yeah, right. So the first one, so you're looking at the base of the same. So you're looking at the 16 and the 3, and if you multiply 16 and 3 together, you do get 48 in your answer. And
yeah, and you just leave the base the same.
And the answer is in the same base. So if you have a look at all the ones that have a yes, I've got the bases are always the same. 9 times 4 is 36. And if I have a look at number 5, I think the bases are the same here. The answer has the same base, and 16 times 3 is 48. Okay, Emma, so you think that if you add the logs of two numbers where the base is the same, you simply multiply those numbers together. Is that what you're saying?
Maybe. I don't know. Yeah.
It looks right, doesn't it? So if I have a look at the others, I can see that on number 2, the bases are all different. So that could be a reason why that's not correct. If I have a look at number 4, the bases are the same when I'm adding, but there's a different base in the answer, and that is not correct. And if I have a look at the last one, those two big numbers have been times together, 121 and 2, but of course the bases are different. The base is different in the answer. So, okay, Emma, let's see if you're right. Okay, I think you might well be right, actually. Now, what I want you to do is I want you to consider two things or two statements that actually we can work with really easily. So the title is the multiplication law. We're going to look at the multiplication law, which is what you get when you add the logs of two numbers together. What I'm going to do is I'm just going to get rid of my second statement there. All right. So we're going to consider log to the base 10 of 100 and log to the base 10 of 1,000. Because you guys know what the answer is to those already. Now, if I look at these two statements, I definitely know that log to the base 10 of 100 is 2, because 10 squared is 100. And I definitely know that log to the base 10 of 1,000 must be 3, because 10 cubed is 1,000. So that means that I can write 10 squared is 100, and under the other one I can write 10 cubed is 1,000. So they are statements that I know to be true. What I also know to be true is that 100 times by 1,000 is the same as 10 squared multiplied by 10 cubed. And what we know when we multiply numbers that have the same base, we know we just add the powers. So we know that ought to be true. We know that that works. Okay. Now, if I were to do, let's scroll down a little bit. If I were to do the log of 100 times by 1,000, bearing in mind I should write log to the base 10 in there, because that's what I'm working with. I know that 10 to the power of 2 plus 3 is the answer to the log 100 times 1,000. So I'm going to write in there 2 plus 3. I think that works. 10 to the power of 2 plus 3 gives me the answer to 100 times 1,000. I know that's right because I've done it above. But I also know that 2 is the same as log to the base 10 of 100. So I'm also going to write down there log to the base 10 of 100. I also know that 3 is the same as log to the base 10 of 1,000. And I'm adding those together. And so I can see very clearly now, I should see very clearly, that log to the base 10 of 100 plus log to the base 10 of 1,000 is log to the base 10 of 100 times 1,000. So I'm going to write that above where I started. And so Emma, I think you're absolutely right. I think that if we had log to the base, well, it doesn't have to be a base 10, it could be anything really. If we had log to the base a of a number, x, and if we had log to any base, but the same base of a number y, I believe we could say that's the same as log to the base a of x, y. But maybe we should prove this, I think, because we haven't proven it so far, we've just shown it. So how do we show it to be true? Okay, so what I'm going to do is I'm going to scroll down a little bit. And we've got the multiplication law of logs. And the multiplication law of logs is what I just wrote. It is log to the base a of x add log to the base a of y is log to the base a of xy. And I'm going to take you through a little proof now.
Do we need to know this proof? Or...
I would say it's really good for your understanding of logs to know this proof. And if you were asked about it, you would know why. Okay, I'd say that your understanding of logs will help you with the proof. And so, yes, I think it's really important to know about this. So I definitely have this in your notes. Okay, so what we started off by doing is we started off by taking the individual terms in our addition. So I'm going to start off by saying that log to the base a of x is a value. It can be any value I like. Let's call it m. And that means that a to the power of m must equal x. So any log statement I can write as an index statement. Okay. Likewise, I can write log to the base a of y is a different value. Let's call it n. And that implies that a to the power of n must equal y. Right. So what I did next was, oops, running out of time. Okay, after this we're going to have to end the meeting and rejoin. Okay. Now then, what I can say next is I can say that x multiplied by y is going to give me a to the m multiplied by a to the n. And because we already know that we add the powers when we multiply with the same base, that tells us that xy must be equal to a to the power of m plus n. Scroll down a little bit. Okay, now that's quite a nice little statement. And from there, we're going to change that back into logs. So this time, we know that if I have a log to the base a of x, y, the answer is the power of a. That's just our knowledge of rewriting an index statement as a log statement. And then if I go back and think about what m actually was, well, m was actually log to the base a of x. And if I think about what n was, well, n was log to the base a of y. It's quite a nice little proof, this. Therefore, I can say that log to the base a of xy is log to the base a of x and log to the base a of y. And that is the multiplication law, which we've just shown to be true. Now that should all be in your notes. And because we're running out of time, as soon as you've got that down, please leave the meeting and then we'll rejoin in a couple of minutes' time. Thank you.
Miss, please could you scroll down?
Yes, of course.
Thank you.
That's all right.
Oh, sorry. Yeah, never mind. Thank you.
That's all right. Right, leave the meeting, end meeting.